Number 13 is exploring some somewhat obscure vocabulary. They want to know where the activated complex or transition state is. The answer is number 3. The reason is because if you imagine that if you have a reactant that looks like this and another reactant that looks like that, as they become the products, let's say the products, one of them looks like this, kind of like a single displacement reaction. They swapped one and you get a sort of a mixed molecule. Well, you can imagine that the transition state is that rare moment in time where they're about to do the collision. So this thing is about to run into that thing, and right when they collide, there's this moment where all three of them are together. It's very high energy, it's very rare, and that's what's called the activated complex or the transition state. So I think the answer would be 3. In number 14, it's looking a bit like a Hess's Law problem. We'll see. Usually I like to number these 1, 2, and 3. We've got a reaction that we're trying to find the delta H for, so I look for C2H2, I guess that is. It's in reaction 3, but this reaction needs to be reversed. And I would recommend rewriting it down, but it needs to be reversed, and the stoichiometry is fine. There's 1 mole here, there's 1 mole there. So our delta H that we'd be using for this reaction would be negative 230 kilojoules per mole. Then I skip O2 because it's in more than one reaction, and I go to CO2. CO2 is in reaction 1. It is on the correct side, it's a product, but it needs to be 2 moles up here. So I've got to multiply everything in this by 2 moles. So the delta H that I'm going to do here is going to be twice that amount, which I guess would be negative, well, 780, is that right? I think that's right. And then, so we've done those two, then we go to H2O. H2O is only in reaction 2. It is on the right side. It has the correct stoichiometry, so I think this one is fine as it is. And then our job is going to be to add those up. As always, the reason I recommend you write them down is because you want to make sure that everything cancels properly and gives you what you want. Like, for instance, the thing I'm most concerned about here is the 5/2 O2. This reaction we reversed, that reaction we left as is, and this one I believe we doubled, right? So it was 2, 2, 2, and I'm just seeing if the oxygens are going to work out. This one was backwards, but there's no oxygens in it. This 2 here would be 4 halves, and that adds to that half to make 5 halves. It looks reasonable, so I think you can just add them up. And so I get A for the answer. Moving on to number 15. In which of the reactions is entropy increasing? Remember, entropy is delta S. We're talking about order and disorder. If entropy is increasing, it is positive. We should see more moles of gas, more moles in general. So I'd say A is definitely out because it has 2 moles of gas going, or actually 3 moles of gas going to 2 moles of gas. Definitely that is not increasing entropy. Let's see, this one you got 2 things going to 2 things. That's a little bit mysterious. Matter of fact, you have 2 moles of gas going to 2 moles of gas. That one's going to be roughly breaking even, so I think potentially not. C, you've got 2 moles of gas going to 2 moles of gas, but you have 2 separate particles becoming kind of one-ish particle. I think that's definitely not increasing entropy either. But D is looking pretty darn good here because you have one thing breaking into 2, you have 2 moles of gas turning into 3 moles of gas. I'd say D is the correct answer. On to 16. When pure sodium is placed in an atmosphere of chlorine, the following reaction... Sorry, I just realized I didn't have my microphone right on me. So in any case, we've got this reaction. They want to know which of the following correctly identifies the values of these things. Let's see. Well, we can probably take a stab at delta S because just as we saw in the previous problem, if 2 moles of something becomes 1 mole and you're losing a gas, that is definitely unfavored entropy. I think that's going to be negative entropy. Then if we're going to figure out delta H, do they give us any hint? When pure sodium is placed in an atmosphere, the following reaction occurs without addition of additional energy. That's a little redundant. Well, no, they didn't give us a lot of energy. I think they say if it occurs without the addition of additional energy, I have a feeling they're saying it's spontaneous. I want to say delta G is negative. Now, we could see if we could rule some things out. Delta G is definitely not positive because it's spontaneous. So we're down to B and C, and we know delta S is negative. So that doesn't divide it. We do have to figure out entropy, or enthalpy. So I usually think about things in terms of the Gibbs-Helmholtz equation. They said it occurred spontaneously, so we know delta G is negative. In order for it to be spontaneous, we can't have both of these terms be unfavorable. Since we already established that delta S is unfavorable, that means this has to be favorable, which is an exothermic process, so that's negative. So now we know delta H is negative, and the answer looks to me like B.